Alright, so we have a block starting at the top of a ramp. They give us the initial velocity is at rest, so it doesn't have any initial kinetic energy. They give us the mass of the block is 12 kilograms. The length of the ramp is 10.5 meters, and the ramp makes an angle of 30 degrees. So to solve for the height, which we'll need, it's just the length, the hypotenuse, times the sine of theta. And 10.5 sine of 30 comes out to 5.25. So in part 1 they have us finding the speed of the block at the bottom of the ramp. The easiest way of doing this is to look at what we have at the beginning. So the energy that we initially have is gravitational potential energy, and at the bottom of the ramp the energy that we have is some final kinetic energy. At least final in the sense that it's at the bottom of the ramp. So it wants the speed at the bottom of the ramp. Okay, so we'll expand our equation. We know the equation for potential energy is mass times gravity times height, and we know all of those numbers. And then the equation for kinetic energy, well, that is 1/2 the mass times velocity squared. So we'll find out really quickly that we don't need the mass, it'll reduce out of our equation, and we can clean it up a little bit to solve for v. So we get rid of mass. The 1/2 will move to the left-hand side, so that's going to give us 2gh is equal to v squared. And at this point, this equation should look familiar because we've used it countless times before. Velocity is the square root of 2 times gravity times height. So at that point, we can just plug in our numbers, and we should get velocity is the square root of 2 times 9.8, and then my height comes out to, so times 5.25. 2 times 9.8 times 5.25. Okay. So my velocity down at the bottom of the ramp will be 10.14. And that's our answer for part 1. For part 2, we're trying to find the coefficient of friction. And now we're going to use the second part of the motion where it's sliding along the bottom of the ramp. So in that case, that we are given the distance, and that is 29.5 meters. And that's the only new information we need. So at the bottom of the ramp, it's going to have some new initial kinetic energy. Let's just call that, let's keep with the color code from before. So it has some kinetic energy at the red dot. And we know what that kinetic energy is in the sense that we know the velocity now, and we know the mass, and so that's equal to 1/2 mv squared. One-half mv squared. There. Okay, now to get rid of that energy, we're going to have to do work. And the work is just going to be equal to our force times our displacement. Okay. Now, if I expand on that a little bit, the force that's causing the block to slide to a rest is the force of friction. And if I expand the force of friction, it's on the flat section, so the normal is just mass times gravity. So let's expand out everything. Our kinetic energy, 1/2 mv v squared is going to be equal to the force of friction, which is the coefficient. Our goal is to find that, times mass times gravity. That altogether is the force of friction. And then that times the distance that the block slides. So just like last time, we're going to find that the masses will reduce out. So mass has gone from that side, mass has gone from that side. And we just need to clean this up to solve for the coefficient for mu. So at this point, it's just algebra. So mu is equal to, now if I take what I already have on the left side, we have v squared, and then that's over 2. To move d and g to the left-hand side, well, to this same side, we're going to end up dividing those, so they're going to join the 2 on bottom. So 2 times gravity times distance. That's a compound denominator, so that all goes in parentheses. Okay, we know our velocity. We can plug in these numbers. So our velocity is 10.14 squared, and that's divided by 2 times 9.8 times the distance, my distance being 29.5. So mu would be equal to 0.178. 0.178. And that'll be our answer for the coefficient. Now, interestingly enough, if we had wanted to simplify the equation even further, we could have substituted in our equation from before, which would have been this guy, in place of v squared on top. And that does something really interesting. So the radical will go away. We have 2gh on top, and we have 2gd on bottom. The 2g's would have canceled out, and the further simplified equation for the coefficient, we could have also done just the height divided by the distance. So if you want to try that out, that will give us the same answer as well. That's a much easier calculation. Sometimes it's interesting how things simplify and becomes really, really easy. Alright, anyway. For the last part, it wants the magnitude of the mechanical energy that's lost due to friction. Well, that is probably the easiest thing, because we already know, the work done by friction back in part 2. We didn't actually solve for it because we simplified our equation, but we know that that work that was done was equal to the original kinetic energy, or which was equal to the original potential energy. So you could solve this however way you want. We just need to figure out what was the starting energy that we had at the beginning. So that's just as simple as mass times gravity times height. And we know all those numbers, so that's just 12 times 9.8 times my height came out to 5.25. So for the final part, work would be equal to 617.4. 617.4. And that's in joules. Okay, so that's our final answer.